So power system, starting off with power system, it's a network of components used to supply, transmit and use electric power. So main components, you have generators, transmission lines, distribution lines and loads, equipment that consumes power. So if you look at typical generators, what's the usual voltage they generate power at? Generators generate voltage at what voltage levels usually? Does anyone know? Typically medium voltage, 11 kV, 22 kV, maybe 33 kV, medium voltage. Sometimes you might have low voltage generators but smaller size that are used for households, that are used during maintenance jobs or in industries. But yes, you're right as well, Hayden, typically medium voltage. So in terms of history of electricity, 1881 AC generation using water wheels in Godalming, England. 1882 DC generation by Edison Electric by steam power in Pearl Street, New York. Now this plant was functional for a long time and Edison was a pro DC man. Has anyone heard of Tesla? Nikola Tesla? Well, Tesla and Edison, well, Tesla was younger than Edison, but Tesla was an AC man and Edison was a DC man. At one stage in their life, they worked together, but they didn't get along. And there was this intense rivalry between Mr. Edison and Mr. Tesla. At one stage, it got so bad that Edison had a demonstration in New York, I think, where he had AC. He got an elephant. He electrocuted the elephant, killed the poor creature. He just wanted to prove to the public how bad AC is. But that was 1880s. Gone are those days. Now, most of the power generated, transmitted and consumed is AC. So there is a PDF document here on some information on the Pearl Street plant. And in terms of war of currents, widespread use of AC power and transmission over long distances due to the efforts of Westinghouse and Tesla. So there is a link here on war of currents, which also gives you some background between DC and AC. Current networks are a complex interconnected system with several generating stations connected to a transmission system. Now the more common ones are thermal, you also have hydro, you have nuclear, which is a smaller proportion, possibly 5 to 10% of world generation, wind, solar and so on, geothermal, tidal, small proportions. Gas turbine also accounts for a fair bit. Gas, hydro, thermal, fossil fuel-based sources account for a fair bit. Sub-transmission and distribution systems. Now, sub-transmission refers to usually 66 kV, 66 to 132 kV. Right? This is sub-transmission. All right? You could also have 33 kV in that range. All right? Transmission, on the other hand, is 132 kV and above, and distribution is 11 kV, 22 kV, or lower voltages. You have industrial, commercial and residential consumers, and you can have embedded generation. A typical example for embedded generation is a diesel generator in a factory or solar panels on your rooftop or a wind turbine in a windmill. Now AC networks have some benefits. They operate at higher voltages. All right. Is everyone familiar with the basic theory of power? Equation for power? Is everyone familiar with this equation? Now this is a three-phase power equation. So three-phase power is square root of 3 times the line voltage multiplied by line current multiplied by the power factor. Is everyone familiar with this equation? Can I see some responses, smiley face or yes, or if you type your responses or raise your hand or whatever. Excellent. Alright, so what happens if your power is constant? Alright, if you step up the voltage, if your voltage is higher, what happens to the current? Current reduces, absolutely. So if you increase voltage 10 times, current reduces by how many times? If you increase voltage 10 times, current would reduce how many times? Current reduces by 10 times. For the power to be constant, a 10 times increase in voltage will mean current reduces by 10 times. Does everyone agree? Because if your power factor is constant, square root of 3 is constant, power is constant, proportionate increase in voltage causes proportionate reduction in current. And remember, your losses are I square R. So a reduction in current, the losses would be 100 times. 10 times reduction in current, the losses reduced by 100 times. So losses reduces voltage drop. So voltage drop is current multiplied by resistance, of course, resistance of the line. Lower the current, lower the voltage drop. And if your current is lower, what happens to the conductors that you use to carry current? What happens to the conductor size? Smaller. Yes, excellent. So they permit bulk power transfer. You also have transformers that step up the voltage at the source end, reduce the voltage, lower voltages at the load end for safety and economics. So generators generate at medium voltage. You have step up transformer, step up to higher voltages. You have transmission lines, zone substation to step it to sub-transmission voltages, sub-transmission lines. Then you have your distribution substations, pole-mounted transformers, reduced to low voltage to houses and so on. So this is generation, transmission at higher voltages with a step-up transformer, sub-transmission, medium voltage, low voltage distribution. So what would you classify in terms of low voltage? Anything less than 1000 volt AC or 1500 volt DC is low voltage. Anything above is high voltage. Alright. So this is the safety definition. Alright. The safety definition is this. Alright. Anything more than 1000 volts is HV. Anything less than 1000 volts is LV. However, in industry, you might find you have low voltage, medium voltage, and HV. These are industrial terms. Low voltage is typically maybe less than 1.1 kV, typically. Alright. Medium voltage is between 1.1 to 33 kV, and high voltage is anything over 33 kV. Could be 66 kV sometimes. So these are the industrial terms, while safety uses this definition. So in terms of the IEEE 141 standard, anything less than 1000 volts is low voltage, medium voltage is 1000 to 100 kV. As I mentioned, it could be 33 kV or 66 kV or 100 kV. Anything over 100 kV is classified as high voltage. Now this is a 330 kV switchyard. You have your isolator, your circuit breakers, your CTs and isolators, and your conductors, bus bars. So in terms of your generator, it generates power at medium voltage. You have a transformer to step it up. Transmission lines transmit at higher voltages. Alright. Then you have step down transformer, transmit at sub-transmission voltages, medium voltages, distribution substation to distribution lines. Then you have pole-mounted transformers for medium voltage to low voltage. Another configuration, this is showing you the schematic. Generators step up the power through transformers, transmission lines, high voltage zone substation, 66 kV step down, medium voltage lines, transformers from medium voltage to low voltage, exactly the same. Different voltage levels are listed here. Low voltage supply, distribution voltages, sub-transmission, transmission, and generation. Alright, is there any doubts or queries so far? Is everyone comfortable with the page, with the slides and so on? Any doubts or queries? Alright, typically rock, you use different terminology. Well, transmission substation, alright, typically refers to where you transform to transmission voltages. So from generation voltage, medium voltage, you transform to 132 kV or 275 kV. That's a transmission. While a zone substation, I think you are referring to a zone substation. A zone substation steps down from transmission voltage to sub-transmission. Alright? So transmission substation will be, for example, if I write it down in a new page, right? So transmission substation might be something like a 22 kV to a 275 kV, right? For transmission purposes. While a zone substation could be stepping down, alright? Stepping down to a lower voltage, right? Right? 275 to a 66 kV and so on. Does that answer your question? Okay. Switching and isolation equipment. You have circuit breakers, disconnectors and control gate. Has everyone seen circuit breakers before? Has everyone seen low voltage air circuit breakers or vacuum circuit breakers or SF6 circuit breakers before? Alright, excellent. Disconnectors, also called no-load switches, and control gate. They are all different types. Yes, Peter. Air circuit breaker for low voltage, VCB for medium voltage, SF6 for medium voltage or high voltage, different types, yes. Conductors, you have bare conductors, insulated, you also call them aerial bundle conductor. Is that the same terminology you use in the United States, Peter? Here in Australia, the insulated conductors are called aerial bundle conductors for low voltage. You also have covered conductors called CC, covered conductor for medium voltage. Not sure if it's the same terminology, should be similar. You also have underground cables. Circuit breakers make and break currents, circuits, remote command for operation. You can have a protection system, a relay, an instrument transformer system that gives signals to the breaker. So relay senses the fault, initiates a trip command. Interrupts high current in the event of a short circuit. Short circuits can happen due to insulation breakdown, can be between light conductor and earth or between phases. The relay gives a trip command. Some breakers have built-in protective devices. Can you name some examples of circuit breakers that have built-in protection? Don't need a separate relay. What type? Yes, type could be MCB, miniature circuit breaker, or molded case circuit breaker. Does everyone agree? Merlin-Gerian, I suppose, is the brand. ACB in certain circumstances, yes, absolutely. The circuit breakers must interrupt currents. That can cause arcing between contacts. Arc needs to be quenched quickly. What happens if you don't quench the arc? Current flows through the arc. The fault is never extinguished. The breaker will fail, the system will fail. You need to quench the arc because arc forms a path for the current to flow. So in terms of quenching medium, you have air or air blast, oil, SF6 and vacuum. Has anyone heard of air blast before? Has anyone heard of air blast before? Yes, what voltages would you use air blast circuit breaker? What voltages typically? Yes, very high voltages, even much more than 66 kV Nicholas. So air blast is used for higher voltages. It's an old-fashioned system. You don't use them anymore. They were common in the 70s. Air is low voltage, air blast is high voltage. The difference being you use pressurized air. Air has limited insulation properties. By using high pressure air, you are improving the insulation performance. These need a compressor plant and so on. Complex. Oil, also not very common now. Very common in the 1940s, 50s and 60s, 70s also. Not very common. Issues with maintenance, hydrogen, explosion, leakage, contamination and so on. SF6 very common, especially for high voltages. And vacuum for medium voltages. Yes, good question, Nicholas. SF6 is a controlled gas. It is legal, but it is controlled under the Kyoto Protocol. That's an environmental protocol. So every organization that uses SF6 needs to document SF6 quantity on the network. Alright, so wherever you are, if you are based in Brisbane, Queensland utilities that have SF6 switchgear need to report it, need to record it, report it to the government. And you need to ensure you don't release SF6 into the atmosphere. It is a greenhouse gas, alright? It is a greenhouse gas, much more worse than carbon dioxide. Depletes the ozone layer, much more worse, alright? So you can use it. Yes, it depends on the government. Well, your options are somewhat limited for higher voltages. If you want a really compact switchgear suited for higher voltages, you need to use SF6. You might have seen, if you go around Brisbane, there are these ground-mounted pad mounts. They're called pad mount substations. They use ring main units, RMU switchgear, and they are SF6. They're not breakers, they're just switchgear, but they have SF6. Why? Because they are compact. Suits a suburban environment, really small, compact, and so on. And also for higher voltages. So SF6 has its merits, and to be fair, most manufacturers design the SF6 to not have any leakage in terms of the switchgear design. The leakage rates are very small. Of course, there will be leakage from time to time, but SF6, yes. Well, if we go back, we had, this is a SF6 breaker, high voltage SF6 breaker, alright, used in a substation. So this portion here is the insulator. So this bottom portion is the insulator, this the support, and here this is one in, out. Here is where the contacts are. Inside this chamber you would have the contacts, alright, insulated in SF6. There is your operating rod. The operating rod goes through here, the operating mechanism there. So this is the SF6 breaker. This is the circuit breaker. And in terms of switchgear, if you actually Google for Schneider RM6, right, I'll just write it down for benefit of people. If you want to Google Schneider RM6 or ABB SafeLink, alright, that shows you ring switches insulated with SF6. So you can have a look. Okay, I'm happy to use red, that's fine. Alright. Is everyone comfortable with red? Okay. I might actually thicken it a little bit. Okay. So far though, whatever I've written in black, could everyone see what I've written in black so far? Okay, excellent. Thank you. So this is the switchboard. This has vacuum inside. So you might have vacuum inside, vacuum circuit breaker. You have relays and so on. Alright, power lines overhead. Overhead transmission and distribution lines can be cross-country, rural or suburban. Now in Australia or bigger countries, Canada, United States, many countries in Europe, Asia, China, you have overhead lines because it's very expensive to have underground cables. The small countries, short distances, cities, underground is fine. Long distances, you need overhead. Conductors, we use conductors, ACSR. ACSR stands for aluminium conductor, steel, reinforced. Alright? So it has aluminium strands, center strand is steel for strength. You can also use all aluminium conductors which are not as strong, but in terms of corrosion performance these are better. In terms of stringing tensions, longer spans, these are better. Use insulators, different types, porcelain, glass and composite, silicone material. Structures, you can use timber or steel or concrete, different types of poles, and you have earthing, aviation warning, line fittings and so on. So this is a transmission line. These are insulators here to insulate the conductor from the tower. Those are your conductors. You have your foundation, you have proper earthing. In case of insulation failure, the conductor will transmit the current to the tower, which is dangerous because this is metal. So if you have adequate earthing, not only will you provide a path for the fault current, but also allow protection system to send support. These are not typical in a lot of countries, these types of poles, concrete. The more common ones are timber poles. If you look at Australian statistics, there are millions of timber poles. I think 5 million timber poles. That's a fair bit. In New South Wales alone, there are more than 2 million timber poles. And timber poles account for 90% of the poles here in Australia. Similarly, United States, Russia, Europe, a lot of countries, timber poles would form the major chunk of the pole population. Timber poles, timber crossarms and so on. Concrete and steel are more expensive, less common. Cables are used in CBD, Central Business District, used for exposed line poles hazards due to proximity. Industries use them for distribution. In terms of installation, it's expensive. Also, if there is a cable damage, although it is unlikely, less common than overhead lines, it's hard to find it out. However, you have lower failures, lower maintenance, and in terms of environmental issues, you're not prone to lightning storms or other issues that overhead lines are subject to, bushfires and so on. Types of distribution, you have radial system, radial with redundancy, loop or mesh. We'll cover each of these types in the next few slides. So what is a radial distribution? Radial means a single feeder where if the feeder fails, entire system loses power. It is not desirable where you have industries, factories, hospitals and so on. So if you are running a factory on a radial feeder, what could you do? If you have a radial line powering a factory, you want production to not be affected, what could you do as a backup? You need to do something locally at the factory, and you might have to install, add another feeder, which is expensive, if you have to contribute, or have a small generator just for the critical loads. Absolutely. Yes. Redundancy. Redundancy means ensuring alternate supply. So you can have a second feeder or you can have a generator for part load. So you can have 100% redundancy with a spare feeder, or you can have a local generator for part load. Reduces interruption time. Types of redundancy, selective and looped. So this is a simple radial where you have one line. This symbol is a circuit breaker symbol. Incoming circuit breaker, outgoing load circuit breaker. You have your transformers and other loads. If this line fails, all the loads are out of supply. On the other hand, this is radial but with a redundant system. You have a second feeder. Alright? So two sources. You run on one, if one fails, switch to the other. You can have automatic switchover. This is more expensive. Selective redundancy, two feeders to each load. One feeder you use at a time. So you use one at a time, the other is not used. You can have automatic changeover. If one fails, change over to the other. Reduces time of interruption, but it is more expensive. You only use one at a time. This is a symbol for a transformer. Alright. These are your loads, breakers, changeover system, the switch. And ring type. Ring type is a very common arrangement used by utilities. Alright. Where you have interconnected system. Your loads are connected in such a way that If this end has issues, you can supply from the other end and supply the load. So if you have to isolate this end, you can supply from the other end. So it looks like a ring where you have interconnections for reliability, ease of maintenance. So it's the preferred approach by utilities. You can have selective closing of isolators, detect faults, easy to extend the ring for additional loads. Supply can be restored to customers without waiting for fault detection to be repaired. Automation possibilities for restoration. You can have automatic schemes. Spur. Now, if you are based in rural areas, you will hear this term, spur. Now, what is spur? Spur is a radial line taken from a ring. So you might have a ring like this, and if you are taking a radial, say 50 kilometers, if you are taking a radial line onto a customer in a farm, that is called a spur. So spur is an extension from a ring. Why do you do spur? Because you don't want to spend the money to extend this ring. If you have to take a ring to the farm, it will be expensive. So you're just taking a single line to the farm, a radial line to the farm. It avoids the need for extending the ring. Downside, lack of redundancy. Mesh is similar to ring, but it is more complex, used in transmission systems, and protection is quite complex, really complex, used for big cities or transmission systems. So this is a typical mesh where you have different reclosers, circuit breakers, transformers, a complex interconnected jungle which is hard to manage. You need to use expressive automation, protection, communication systems used for transmission of big cities. For reliability, you can also have duplicate feeds for industrial distribution. So you can have duplication for different levels. For higher availability, it's expensive but flexible. You can have bus sections with couplers, or duplicate bus, or duplicate feeders. Redundancy can be achieved at a primary level, a single supply feeder with redundancy at plant level. You can have redundancy at the plant level. A duplicate supply, two feeders. Use two feeders. Or you can have redundant transformers with single supply or duplicate supply. You can also have redundancy by LV interconnection, so redundancy through interconnecting the low voltage system. You can have two transformers with LV bus, three transformers, multiple transformers for reliability again, redundancy. So this is a secondary system redundancy, alright. So what you have here, you have, this is one feed, this is the second feed. At any given time, you might only run one, and the other one is off. But if there is a fault, right, if there is a fault there, then you can run using that. And you keep the bus coupler closed so that if you are running through that, it supplies the loads here and here. Or if you are running from that side, you are supplying the loads on either side. If you want to run both though, you might leave the bus coupler open. So this is secondary system redundancy. You can also have low voltage interconnections as shown here. So you have transformers, you have interconnections on the low voltage end. So secondary type bus for low voltage redundancy, interconnections. Another example for redundancy, what you have here, you have two transformers. And why have you connected this in zigzag? Why does this supply go here and this supply go here? Can anyone give me the answer? Why can't we just connect them on straight lines? That coming to this and this coming to this. Why do you have this configuration where this side feeds this panel and this side feeds this panel? Maintenance, reliability, changeover, absolutely right, yes. If for example you had issue with this one, alright, by closing this, this will be closed, and closing this, you are supplying both loads. On the other hand, if you had issues with this one, Then by closing this, you are supplying both loads. So for maintenance purposes, if one is off, you can run the other one to supply all the loads. Changeover, maintenance, redundancy, reliability. So what should you consider as the most important for a power system? So, simple question, what would be your answer? What's the most important thing before you start anything in most organizations? Yes, well, reliability is important, but before reliability, safety, yes. Safety comes first, second comes reliability, alright, and third one is value for money. Alright, so safety, reliability and value for money are the key objectives. Safety is always number one, never compromise safety.